So, 2 days of step functions, piecewise functions, quiz, Friday the 3rd. All right, today we're going to look at step functions. Step functions can actually be called many different things. The first one we're going to look at is called a greatest integer function, and I really think this name is kind of deceiving. Because what greatest integer function means is we're looking for the greatest integer that is less than or equal to something. The greatest integer that is less than or equal to something. Well, when I think greatest, I think bigger, not smaller. But it ends up being smaller. So this is commonly referred to as a rounding down function. Rounding down. Now, this goes against everything you've learned since elementary school. In elementary, we taught you to round to the nearest, and you like that. So rounding down doesn't make much sense. I'm okay with that, but it's easy. It's easy once we get our brain out of round to the nearest mode. Okay, so we have a couple symbols for rounding down. It can be the double brackets, which you don't see that often in text. It can be the single bracket, or it can be this one. This one's also referred to as a floor. Rounding down would be floor. What do you think rounding up would be? Ceiling. That's right. Okay, so tomorrow we're going to add rounding up to it. All right, so we're going to start with this lovely number, 3.4. And since 3.4 is between 3 and 4, and we're rounding down to the nearest integer that is less than or equal to the number, what would 3.4 round down to? 3. I like to kind of visualize it on a number line. Well, that's an interesting number line. Let me try again. That looks nothing like a number line. All right. So if I had my little number line and I was visualizing 3 and 4, and 3.4 would live about right here. If I round down, it obviously rounds down to 3. Now, the same thing would happen to 3.85. My brain does not want to do this. It wants to round 3.85 up, because 5 or greater, we always round up. But this is a rounding down function. So even though 3.85 lives much closer to 4, we're going to round it down to 3. Okay? Now, positive numbers, we can figure out. Negative numbers are a little tricky, though. Like this one, negative 7.25. So negative 7.25 would live in between negative 7 and negative 8. Negative 7.25. So if I round it down, it would round down to negative 8. So it lives between negative 7 and negative 8. So that's what we're going to look at first. We're going to round down. Practice rounding down. So even though we want to round to the nearest, we're not going to. This tells us to round down. So if we round 5.7 down, it rounds to 5. Now, square root of 5. I don't know exactly what that is. I kind of approximately know what that is. But I know it's between what two integers?
Which two?
2 and
2 and 3. Because 5 is not a perfect square, but 4 is, and the square root of 4 is 2. And the square root of 9 is 3. So 5 is in between those. So 5 is in between 2 and 3. If we're rounding down, it's 2. So this becomes 2 times 2, which is 4. Okay? Now, the next one is 3 pi. Well, pi is an absolutely wonderful number. And you guys know a nice little decimal approximation for pi. What did you learn in elementary school? 3.14. Okay, so if we did 3 times 3.14, that's what we have here. 3 times 3.14. That's 9.42, right? Approximately.
yeah.
We just go down to 9, right?
And then we just go down to 9.
Okay.
You got it.
Can I just say, like, pi is going to be 3?
Yes, you can, because we're rounding down.
Okay, that's good.
Okay, now here's a negative one. Don't let it trick you. If we're rounding this down, what would it go down to?
Negative 7.
Negative 7. All right, 0.2, what would it go down to?
0.
0. All right, what would negative 9.1 round down to? Negative 10. So 5 times negative 10 is negative 50. Okay, so the next thing we're going to look at is, all right, if we thought about this as a function, what would it look like? Okay, so I can use the double brackets, the single brackets, or this floor looking. But as a function, what would this look like? All right, I don't want you to write this down, but I want you to hang with me on the thinking through this process. So I'm going to start with 0. If I plug 0 in, 0 is an integer. So if we're rounding it down to the greatest integer that is less than or equal to, it would just be 0. So this would be a point on this graph. All right? I'm going to do another point. 0.001. 1,000. What would that round down to?
0.
0. All right, how about just 0.1? What would it round down to?
0.
0. All right, how about 0.22? What would it round down to?
0.
0. How about 0.38?
0.
0. Okay, 0.41.
0.
0. How about 0.56? 0. How about 0.67?
0.
0. How about 0.7? 0. How about 0.88?
0.
0. How about 0.9999999?
0.
0. Okay.
What do you know?
1.
Not.
Not 0. Yeah. What does 1 round to? 1.
I thought I was wrong.
Okay. So you're right. It's not 0. You are correct. So what happens is everything from 0 until I get to 1 rounds down to 0. So how do I graph that? Well, I'm going to start with 0, 0. Let me change this to pink. It's easier for me to see.
It's gonna be weird looking.
Okay, so now I'm going to plot all these points right here.
They're just dots. They're just like dots along the
It
x-axis.
is, but everything along there would. Every single thing along here would, until I get to 1. And at 1, it jumps to right here. So from here to here, it looks like this very interesting little mathematical barbell, where if you went and lifted weights with it, you would probably fall over because this side has a weight and this side's empty. Okay? So a step function makes this really odd looking barbell. Huh. Alright, so now what happens at what? This same thing that just happened here. Because what would 1.1 round down to? 1. 1.2 would round down to 1. 1.6 would round down to 1 until I get to 2. And at 2, I jump up to 2. And then I get my next little barbell. Because the same thing happens. And then I get an open circle and then I jump to 3. And then I go over and the same thing happens. And then I jump to 4. And then I go over and the same thing happens.
So why don't they follow the barbell?
Well, if you look at it, and if I did a good job, does it look like, here we go, does it look like I'm climbing up steps? Yeah? Thanks, I appreciate that. All right, these look like steps. And these are going up. Step function. Now, it's obviously not continuous. Because if I put my finger right here, I gotta jump to get to there. And jump, and jump, and jump. So this function is not continuous. It has something called jump discontinuity. We're jumping. It is discontinuous, and we have jump discontinuity. Now, this is not the entire graph. It doesn't just go this direction. It also goes the other way. Because I could do the same thing with the negative numbers. So these barbells keep going, but I have to put an open one up under this one and go back to the closed one. an open one under the closed one and go back to the closed one. Okay? Now, was I restricted on any x value I chose to plug in? No. I can plug in anything for my x values. I could even say all reals, couldn't I? I could say negative infinity to positive infinity, write it in interval notation, or I can write it as the set of all real numbers. Isn't that what the double R means? Do y'all remember that? Yeah. Now the range. The range is what we get out. When I plug those x values in, what did I get out? I got out 0. And then I got out 1. And then I got out 2. And then I got out 3. And then I got out 4. And I got out -1. And I got out -2.
All those numbers.
Okay?
What did this function want to show us?
What will it show us?
Yeah.
Tomorrow we're going to do application.
Oh, okay.
Yes. Okay, so when we look at these y values, -2, -1, 0, 1, 2, 3, that is the set of what kind of numbers? Integers, that's right, the set of integers. Does anybody know the cool symbol for the set of integers?
No.
All right. It doesn't make sense. You would want it to be I. You would want it to be I, because I, integers. But it comes from the German, and it's a double Z. It's a double Z. Isn't that cool?
How we write it out?
How do you write it?
The best you
Okay,
can.
so there's a really pretty one that I snipped off the internet, but I would write it like this. The double Z. Okay, now, if you're not fond of the symbol, then just write the set of integers. Okay, now there's also another way. Yes, sir.
What does the R look at there meaning?
The double R stands for the set of real numbers.
Okay.
Like a double P stands for a paragraph in English. Double R in math stands for the set of real numbers. Okay. Now another way to describe the range, because it is discrete values and not a continuous interval, we can't use the interval notation. We have to show the braces. It is discrete y values. So another way we could show this is go dot, dot, dot. What are 3 dots in a row called in mathematics? Ellipses, good. All right. And then list your y values. -2, -1, 0, 1, dot, dot, dot. So if you show enough y values to give the pattern, you could do it that way. So there are 3 acceptable ways to write your answer. Make sense? Okay. All right, x-intercept. All right, the x-intercept's a weird one because it doesn't intercept in a single point. Do you see this? That's not a single point. That's a line segment. And a segment represents an infinite number of points. So I can't describe the points unless I use an interval. So, it intercepts the x-axis from 0, that doesn't look like a 0, from 0 until we get to 1. Now, at 1, it jumps. So we have to use a parenthesis right there because it doesn't include the 1.
Hence the open circle.
Hence the open circle. All right, y-intercept. We actually have one little intercept. It's the point 0, 0. Now,
What about 0,
at 0, -1, it's an open circle. So there's not actually a point there. Okay, now this is fun because we ask you on every single problem. But every single step function is neither. And let's talk about why. Because if we thought about symmetry in terms of graphically, one way would be to rotate 180. And if we did, think about what's going to happen with the closed and the open. If I rotate this 180 degrees, it switches. The open end is now on the left side, and the closed is on the right. So odd doesn't work. And the same problem happens when we reflect it, right? If we reflect it over the y, it's not even close to even. So every single one of these is neither. They're all neither. And the domain of every single one of these is this. Because we're not restricted. All right, now there are some things we can do with these functions. I'm going to erase some of this now so I can get my space back. We can perform the same transformations that we did with all of our other functions with step functions. We can vertically stretch them or compress them, which is what the next problem does. We can shift them, left, right, up, down. And we're also going to do one more interesting thing with this one. We are going to horizontally stretch and shrink these step functions, which we didn't do with our others. All right, now looking at this one, where do you think the first barbell should be placed? The first step. Okay, is it shifted up, down, left, or right, Eddie? No, it's not. So we're going to start this barbell right here at 0, 0. Okay, and we're going to go over to 1, and we're going to put our open circle. Because we studied the parent graph, and we know that's how we start. Now, this one is different from the parent graph, and the fact that it has a 3 out in front of our function. So that 3, instead of jumping up 1 step, how many steps do you think we jump?
3.
3. So my next step will not start at 1, 1. It'll start at 1, 3. So here comes my next barbell. Over, open. And then we jump up 3. Over, open.
Do you go over 3?
Nope, just 1. Over 1. And then we go down 3, and we go open, back to closed. So, that 3 out in front is going to cause the vertical stretch. But when we look at it, it's going to change how we jump. It's going to cause us to jump by 3. Got to write the word stretch. All right, domain. There are no restricted x values. My domain is from negative infinity to positive infinity. Now, let's look at my range. I've got negative 3, I've got 0, I've got positive 3, and I've got positive 6. Because for the range, I'm looking at those y values. So I could describe it dot, 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 negative 3, 0, positive 3, 6, dot, dot, dot. Now, in this particular case, I could describe it with words. I could. I don't have to, but I could. This is multiples of 3. Sometimes it's difficult to describe in words. So being able to write the pattern is much easier. All right, this has that same interval for our x-intercept from 0 to 1. And the y-intercept is still 0, 0. And this function, just like all step functions, is neither odd nor even. All right. Whoops. It appears I forgot to erase this. All right. Our next one is 2 minus the greatest integer x, which I could rearrange this order and say negative rounding down of x plus 2. See, these two things mean the same thing. I could have written the problem this way. So, what transformations is 2 at the end is going to shift it up to? Now, what do you think this negative in front of my x does? It does. It makes it go down. Okay, so there's that reflection over the x, and that reflection over the x causes it to go downstairs. There we go. So this plus 2 is going to shift it up 2. So my first little barbell starts right here. Close circle on 2. Over 1 unit. Open circle right there. And because of the negative out in front, I go down when I jump instead of jumping up. Go down. Go down. Alright, so domain is still negative infinity to positive infinity, or you can write all reals. The range this time, when I jump by 1, whether I'm jumping up or jumping down, when I just go by 1, it's going to be all the integers. So you can put your double Z for the set of all integers. You could write the set of integers. Or you could give me the pattern. All these are correct answers. Now this time my x-intercept is shifted over. It is from 2 to 3. Includes the 2, not the 3. But the y-intercept is the point 0, 2.
Why does it say 2 now?
We include the 2 because it's the closed circle. We do not include the 3 because it's the open circle. Alright, so now we have 3 more little interesting examples here. On the first one, can you tell me where this function starts? Where does the closed circle of the little barbell for the step go?
-3, 0, -3.
Okay, so down 3, and then what does this do?
Right.
To left.
Left 2. So my translation point is -2, -3. That's where I'm going to start with my barbell. So solid right here. And then we go over 1 unit, open. And then I jump up 1 because it's positive. Solid over to open. Jump up 1, solid over to open. Jump up 1, solid over to open. Jump up 1, solid over to open. Alright, the really cool thing about step functions, which we can't do with most functions, is we could actually write different equations to represent the same graph. Like, what if I said, what if this were our first step? It would look like this. Wouldn't that be the exact same graph? What if I said, let's let this one be our first step? Then it would look like this. So depending on which step I decide to start with, I can write infinite number of equations to represent this exact same graph. That doesn't happen with all functions. All right, let's take a look at this one. This is different. There's nothing added to the x or added to the y, so we're starting right here at 0, 0. But we have something weird happening, which we haven't done. We have the x being divided by something. Now, when we multiply or divide out in front, that stretches and compresses vertically. When we multiply and divide in with the x to the x, it stretches and compresses horizontally. Now, every time we have an x, we do the opposite. The opposite of adding 2, subtracting 2. -2, 3. So the same thing happens here with multiplying and dividing. What's the opposite, what's the inverse operation of dividing by 2? Multiplying by 2. So instead of my step being 1 unit, my step ends up being 2. It's just a longer step. So for this problem, I would start right here at 0, 0, but I would go over 2 units. to do my open circle. Now I still just jump up by 1 and go over 2 units. And go over 2 units. So when I go backwards, I go back 2 units. And I go back 2 units. All right, so let's take a look. Actually, I just want you to try this one. This is y equals -2. And then we have to round it down. X plus 3 divided by 3 plus 5. That's that equation. Let's see what you can do. All right, guys, where do I start? Okay, -3, +5. How far do I go across? 3. Okay. How do I jump?
2.
Down 2.
Why is it down? It's not. Oh, it's negative.
It's 'cause of the
Sorry,
negative.
I didn't see it. Not nice.
Whoops, that's not 2. That last one was bad. All right, when we jump up or down by 2, every time it ends up being the set of even or the set of odd. And in this case, it's the set of odd integers. So you could write the range for this one. You could just write out the words set of odd integers. Or you could get the pattern.
How to give out the patterns?
For this one, I would start with, I'd probably ... 1, 3, 5, ...